Ok, voy a empezar a compartir.
We need to switch to English.
Yes. Can you see my screen?
Yes.
Yes.
Okay. Well, I will start this last session about the workshop on extended mass distribution of primordial black holes. Okay. And primordial magnetogenesis. In this last talk, I will talk about extended primordial black hole mass distribution with a spike. First, I will give a brief introduction about how to construct this distribution with a peak at any mass and at any pivot mass. And after that, we will have an hands-on activity in collaboration with Joaquín Sureda. Well, the outline of this talk is the following. First, I will give you some brief motivation of why to study these hypothetical primordial black holes. After that, I will summarize some of the main results of extended primordial black hole mass function from a broken power law presented by Nelson Padilla, Joaquín Sureda, Ignacio Araya, and Marcelo Rubio. The last two sessions. After that, I will present how to construct this mass function with a spike, and finally, I will show you some observational constraints for the free parameters of this mass distribution and my summary. Well, the motivation is that now in the cosmological standard model, the dark matter is composed by no collisionless and no relativistic particles. There are many candidates. For example, the WIMPs, one of them is the neutralinos. It is very popular. Other interesting alternatives are the ultralight action, that these particles are bosons that can be described by a scalar field. Of course, these hypothetical black holes form in the early universe, and they can cover wide ranges of masses from 10 to minus 18 to 10 to 15 solar masses. These primordial black holes are a kind of ultra cold dark matter with a high mass. And nowadays, there is a very strong motivation to study this object because the detection of the gravitational waves by LIGO, for example, one of the systems that collide is composed by a black hole, but the secondary component is a compact object in the gap between the massive, the bigger neutron star and the lighter black hole from stellar evolution, and then maybe this compact object can be a primordial black hole. Actually, the collaboration mentioned that in some of these of the papers. These hypothetical objects were proposed from the 60s by Seldovich, Hawking, Carr, and this object can be formed from the density collapse, from the collapse of density fluctuation in the very early universe, mainly in the just after the inflationary epoch. For example, when the reheating finished, and there are many mechanisms that could lead to the formation of primordial black hole, for example, phase transition, also some features in the inflation field. And the simplest way to describe these hypothetical primordial black holes is through a monochromatic mass function. This kind of mass function means that all the primordial black holes are formed with the same mass, and this mass is proportional to the horizon mass and the epoch of formation. For example, here you can see a schematic plot of this monochromatic mass function centered at 10 to minus 14 solar masses. Of course, this kind of monochromatic mass function are modeled, for example, with an approximation of the Dirac delta function or very narrow function describing this peak. Well, in the literature, there are many observational constraints on this kind of monochromatic mass function. For example, these constraints presented by Carr and colleagues. In this plot, they show the mass of monochromatic mass function of primordial black hole, and in this y-axis, they present the fraction of the mass of primordial black holes over the mass of the dark matter density in the universe. They use different physical processes, different phenomena. They are representing different colors. For example, the red lines represent a constraint from the evaporation processes. The blue lines represent a strong lensing constraints on these objects. The green lines, dynamical effects, for example, this heating, because the presence of these compact objects in the disk of our galaxy, for example. And if we combine all these observational constraints, you can observe that there are only two windows where the dark matter in the universe can be composed totally by these hypothetical primordial black holes. This window here and the other one. Obviously, these observational constraints depend on the redshift also. For example, in this plot, Carr and colleagues show the influence of these constraints on depending on the redshift on this quantity F. Well, now the question is, what if the primordial black holes are formed with different masses and not only with a unique mass? In the talk by Nelson Padilla and Joaquin Sureda, the last Monday, they comment about how to construct a primordial black hole mass function using a modified Press-Schecter approach under two mechanisms of formation. The first one is called fixed conformal time. In this scenario, all the primordial black holes with different masses are formed at the same time. In this work, we consider that the epoch of formation is when the scale factor is equal to 10 to minus 26. The other scenario is called horizon crossing. In this scenario, the primordial black holes are formed at different times with different masses, and when the fluctuation size of this object match with the horizon, that means that the lighter primordial black holes are formed before than the bigger primordial black hole. For example, in this schematic plot, you can see, you can imagine this mechanism of formation. For example, here is the scale factor of the universe and the mass of the former primordial black hole. The red line represents the fixed conformal time. In the same epoch, different primordial black holes with different masses are formed, but in the other case, the horizon crossing, the lighter primordial black holes are formed before the bigger ones. Well, to construct this, extended mass distribution, we use the Press-Schecter formalism. This formalism is very useful and widely used to describe the mass function of halo, for example, in n-body simulation, and is given by this formula here. this expression involves many physical quantities. For example, here you can see the mass density of dark matter. And also we have new parameters defined like the ratio of the threshold linear density for primordial black hole formation over the variance of the density fluctuation. This quantity also represent or can represent the height of the peak of the size of the fluctuation. And this delta C, when a fluctuation has a density contrast greater than this threshold linear density, then a primordial black hole can be formed. Well, the variance of the density fluctuation can be calculated using this integral here. There are many quantities also. For example, the wave number, which is related with the size of the fluctuation. And also we have this quantity D is the growth factor, which gives information about how the fluctuation evolve when the universe expands. And other quantity here is this function W, and this is a filter function, for example, to smooth the density fluctuation. In this case, we choose a top hat filter function, but there are other alternatives. And one of the main ingredients to calculate the variance of the density fluctuation is the primordial power spectrum, this quantity here. If we have the functional form for a primordial power spectrum, then we can calculate the variance of the density fluctuation, then we can calculate the new parameters, and after that we can obtain the mass function. Other assumption is that if these density fluctuations follows a Gaussian statistic, this multiplicity function here is given by an exponential, like in this expression here. In the papers that was comment on the last session, we consider a broken power law spectrum. This is a piecewise function given by this formula. This is a power law with a red index for wave numbers less than a pivot wave number k pip, and for wave number greater than this pivot wave number, this exponents becomes blue. That means that this exponent is greater than 1. And here you can observe this primordial power spectrum. In this case, we choose k pip equal to 10. This is this dotted line here. And the red line represents the standard power spectrum, just this part with the exponent is red, and the blue line represents this broken power spectrum. You can see here that there is an enhancement for large wave numbers. That means for smaller scales. And if we introduce this primordial power spectrum in the Press-Schecter formalism, we can obtain this kind of extended mass distribution. I showed you some examples. In blue lines, the horizon crossing mass distribution, and in red line, the fixed conformal time mass distribution. And you can observe here two important free parameters of this distribution. The first one is the M star parameters. This is a characteristic mass where the mass distribution starts an exponential cutoff. And the other parameter is the slope of the mass distribution, this parameter N, which is close related with the blue index here. Well, you can observe that if this index is varied, the amplitude of the mass function change. Well, With this extended mass distribution, we constrain these three parameters, M star and M blue, using the monochromatic constraints. But in that work, we introduce a method to translate these monochromatic observational constraints to extended mass distribution. And we obtain this kind of plots here. You can observe here the slope of this mass distribution and the log of the characteristic mass M star. As mentioned before, the slope of the mass distribution is close related with a blue index, and the colors represent the values of the fraction of the mass density of primordial black holes over the mass density of dark matter in the universe. When this quantity is equals to 1, means that all the dark matter in the universe is composed by primordial black holes. And the interesting result of this work is that we found 4 windows, a combination of the parameters N or M blue and M star, where this happened. For example, in horizon crossing, we found this region here. And it is very interesting because the characteristic mass is about 10 to 2 solar masses, and this mass overlap with the masses estimated by LIGO of the collision of compact objects and the emission of gravitational waves. Now we want to generalize this kind of extended mass distribution. For example, considering the spike in the primordial power spectrum. What is the motivation to consider this kind of a spectrum? Well, in the theory of inflation, there are many inflationary potential which present, for example, bombs or spikes. For example, there is an example presented by Shane and colleagues. This is the scalar field for the inflation potential, and this is an exponential-like scalar field, but at any scale for the scalar field has a bump. You can see the InShot here, and this bump has an amplitude, and this can be translated in a peak in the primordial power spectrum. For example, using this scalar field for the inflaton, these authors obtain this primordial power spectrum, which is peaked at this wave number 10 to 14, 10 to 15 solar masses. Megaparsec to -1. Of course, if I put if the authors put these bombs in the scalar field in other position, well, this peak in the primordial power spectrum will shift. Also, these authors obtain a monochromatic mass function for primordial black holes of this kind. For example, here, this is the observational constraints for monochromatic mass function, like I showed before in the first slides. And varying the amplitude of this bump in the inflation field, they can obtain different amplitudes for this monochromatic mass function. Also, as mentioned before, if we move this bump, we can put this kind of monochromatic mass function at different positions here. Then we want to investigate a combination of monochromatic mass function with the extended one by considering a spike at any characteristic wave number in the primordial power spectrum. How to do that? Well, we consider the same broken power spectrum that was presented by Nelson Padilla and Joaquin Sureda, but now we add a log normal like spike given by this formula here. Here, for example, Kp is the wave number where the primordial power spectrum is peaked. This quantity A2 is the amplitude of the peak, and epsilon is the width of the peak. If I add both terms, I get a primordial power spectrum of this kind here shown in this plot. Remember, this orange line here is the pivot wave number where the spectrum, where the index becomes blue. But now we have other Kp where the primordial power spectrum is peaked. In this example, I put the peak and this value of the wave number 10 to 13 megaparsec 10 to -1. And then I can put this peak at any place of the primordial power spectrum, and then I can use this primordial power spectrum in the Press-Schecter formalism, and I will obtain an extended mass distribution with a feature with a spike and this wave number. Where this wave number is translated to any scales, and the scale is translated to any mass. If I do that, I obtain this kind of extended mass distribution. For example, this is the mass distribution for the horizon crossing scenario. The first, this term and these other terms are the same that those obtained with a broken power law, but now we have an extra term here in this blue square, which depend of the position of the peak in the primordial power spectrum, and also depend on the amplitude, on the width of this peak. When this amplitude A2 is equal to 0, we recover the mass function from the broken power spectrum. In this plot, I show you some examples of this mass distribution with a spike. In this example, I consider this characteristic mass m star equal to 50 solar masses and the blue index equal to 2. And the gray line represents the extended mass distribution without a spike. And I put a spike at different position, for example, at 25 solar masses, 10 to -5 solar masses, and 10 to 10 solar masses. In this example, I use the same amplitude A2, and I obtain this kind of extended mass distribution with a spike. For example, observe this mass distribution, the blue line. The peak is very close to the characteristic mass m star, and in this case, we can observe here a kind of log normal function, or kind monochromatic function, but on the left side we have an extended mass distribution. And then this is very interesting because it's a combination. It's a combination of an extended distribution with a monochromatic distribution, and the monochromatic distribution can come from any feature in the primordial power spectrum, for example, from the inflation field, and the extended distribution can come from the collapse of density fluctuation in the early universe. Well, we have a problem with this kind of extended mass distribution, and this problem is that now we have four free parameters: m star, the blue index, the position of the peak, and the amplitude of the peak. In this example, I put by hand the value of the amplitude A2, but we don't want that. There are one way to estimate a physical value of this amplitude A2, and the procedure is like follow. Given a peak mass, MP, we can calculate...
Sorry, Juan?
Yes.
Yeah, I mean, Ignacio raised the hand. Maybe wants to make a quotation there, or...
Okay.
Yeah. I wanted to ask just that the peak mass is related with the peak in K, in wave number, right? So maybe you can explicitate that relation between the peak in power spectrum and the peak in mass.
Yes. There is a relation between between both quantities. The wave numbers is related with the size of the fluctuation, and we can consider, for example, an spherical region, and we can obtain a relation of this wave number with the mass, and this relation will depend on the mechanism of formation. This relation between M and the wave number will depend if the scenario is horizon crossing or fixed conformal time. In the case of horizon crossing, the relation between the wave number and the mass is K is proportional to M to minus 0.5, and in the case of fixed conformal time, K is proportional to the mass to minus 1/3. This is the relation.
Great, thank you. So just to make it clear then, so because you have an algorithm, right, that's going to kind of post-process a power spectrum, right? So you have a power spectrum that has a smooth component plus some log normal feature, let's say, that encodes an excess in power, like an imprint in the primordial power spectrum. And that you have like a automated algorithm, let's say, that takes this power spectrum and spits out a mass function, right? So actually the parameter of the scale of the peak in the mass function is not the input. The input is the wave number scale in the power spectrum where the peak is located, and the mass depends on that. So when you do the computation, the parameters that depend on which your model depend are the parameters of the power spectrum, not of the mass function, but they're related one-to-one, basically. Right?
Yes, they are very close related, but you are correct. We choose a wave number where the primordial power spectrum is peak, and after that we translate this wave number to a mass. For example, in this mass function here, the constant, the proportional constant to transfer wave number to mass is this constant here, CHC, and you can see the relation or the exact number of this constant in the Surera paper, for example. But you are correct. We choose a wave number where the primordial power spectrum is peaked. After that, we translate this wave number to the mass. At this moment, the amplitude A2 is put by hand, but we don't want to do that. One way to estimate or to calculate the value of A2 is by consider any fraction of the total mass inside the spike. For example, if I ask that in this spike I want to put the 20 or the 30% of the total mass of the distribution, I can obtain the value of the amplitude A2 to get that. And this is a way, a more physical way to give a value for A2. And using this procedure, we can obtain a maximum amplitude A2 because there is a limit to there is a limit of mass inside the spike, because we have to satisfy this relation here, that the addition of the mass inside the spike plus the mass of the extended distribution should be less or equal to the total dark matter mass density, for example. And then this amplitude A2 obviously will depend of the position of the peak. For different position of the peak, I will get different fraction of mass inside the spikes and different values for the amplitude A2. For example, I performed this procedure for this example here for the horizon crossing and fixed conformal time scenario. For this value of the characteristic mass, 50 solar masses, and in this case, I consider the blue index equal to 3.5 for the horizon crossing and 2 for the fixed conformal time. You can observe here that with a more physical value for the amplitude A2, I can obtain a very, very narrow peak. This is a monochromatic mass function. And inside this spike, or inside of this monochromatic mass function, I put about 50% of the total mass of the distribution. And it is very interesting. This is the combination of a monochromatic mass function, but we have an extended part for lighter primordial black holes. And now, obviously, if we ask what happened with a fraction of mass of primordial black hole has dark matter, with this kind of mass function, obviously we expect that this quantity change because the presence of this spike, and we calculate the modification or the changes of on this quantity F using this extended mass distribution. For example, we obtain the following. Show this plot in the x-axis. You can see different position of the peak mass for this m star value, 10 to minus 10 solar masses. The y-axis show the fraction of mass of primordial black holes over the mass of dark matter in the universe. And the colors of the dots represents the maximum fraction inside, the maximum fraction of mass inside the spike. This orange line here stands for the value of this quantity without a spike. And you can observe that if we include a spike, depending of the position, this quantity increase, or also we can obtain that this quantity decrease, for example, in these cases for the peak mass. But it is interesting, for example, for this case here, when the characteristic mass is equal to 50 solar masses and the blue index is equal to 3.5, because, for example, if we put the peak mass far away of the characteristic mass, we obtain that this quantity, PBH, is similar to that obtained without spikes mass distribution. But if we put the peak mass very close to the characteristic mass m star, I obtain that this quantity FPBH increase up to almost 1. That means all the dark matter in the universe can be composed by primordial black holes. And then I can explore all the free parameters of this kind of mass distribution with a spike, and to observe or to try to obtain mass distributions in other regions, for example, of this plot. And then I will explore more about these free parameters of this mass distribution with a spike. Well, my summary is that by considering a primordial power spectrum composed by a broken power law with a log normal term, which represents a spike, I can construct extended primordial black hole mass function with a spike, and this extended mass distribution represent a combination of monochromatic mass function with an extended mass distribution. And this is very, very interesting. Also, we want to explore many many configuration varying the free parameters of this extended mass distribution. But one of the main results that we have observed up to now is that all the primordial black holes can compose the total dark matter in the universe. And if we include a spike, we can expect the more windows of the combination of the free parameters where this happen. Well, that's all. I don't know if there are questions or comments. I will send a link with a code to run this mass distribution. Ignacio.
Yes, so I have a small question, because in the first session, there wasn't enough time to explain the actual statistical algorithm that translates constraints for monochromatic mass functions into constraints for extended mass functions. And it was kind of like the central part of the second part of the activity, but no problem, because you're going to do the same. You're also going to run the algorithm to translate constraints of monochromatic to extended, but considering different mass functions, right? So maybe you could briefly review, maybe not now, but in the hands-on session, what is the actual algorithm that translates the constraints, right? What is it that we do, to convert monochromatic constraints into extended ones, right?
Okay, in this for this kind of extended mass distribution, I use the same algorithm that for the previous session.
Yeah, but the point from Ignacio is that we didn't explain it because the presentation was actually very short. So
yes,
I can explain that.
Yes, I have the scripts. I can show you.
Excellent. Thank you.
What is the procedure to translate these constraints from monochromatic to extended ones?
But maybe just, I don't know, it's an idea, just to explain, I don't know if you have the paper there.
No, I don't have
very
the
briefly
paper.
how to do it, because it's just statistics in general.
Okay, let me to show. I don't include any slide about the method to translate monochromatic constraint to extended one, but we can observe this plot. Here you can observe different lines. For example, the blue lines represent a physical process. In this case, is a strong lensing constraint. This is a filter function, is a statistical function, which takes into account the physical process involved, which depend on the mass of the primordial black holes. But this filter function is sensitive only for a range, for this range of masses, or, well, for any mass, for monochromatic mass function. And then to translate this monochromatic constraint to extended one, we use this filter function, but now we weight this filter function with a mass, with the extended mass distribution. And also we correct, we introduce correction, because now we have an extended mass distribution, and we need to consider, for example, primordial black holes outside of the limits of this filter function. For example, if I have an extended mass distribution covering, for example, masses from 10 to minus 14 solar masses to 10 to 3 solar masses, this filter function only affect, in the case of monochromatic mass function, only affect this interval, but there is a contribution of the primordial black holes outside this filter function, and we introduce a correction. And also, as mentioned before, these monochromatic constraints also affect on different way depend on the redshift where the physical process take place. And also we introduce a correction because the evolution of the mass function, because these primordial black holes, like other standard black holes, can suffer of the Hawking radiation, and then they can evaporate. This evaporation mass depend also of the redshift, and then we expect an evolution of the mass distribution. And then we also introduce a correction which takes into account, for example, the evaporation mass at different redshift, and also, for example, the maximum mass of the distribution that I don't mention in this talk, but I don't know if in the first lesson was mentioned, is the maximum mass of the configuration is, we call 1 pH. And in this way, we can translate this monochromatic constraint to extended mass distribution constraints. Maybe I can download a paper. Sorry. In this part. What is it? Here in this section, in the section 3.2, there is a further explanation of how to constrain, how to translate the monochromatic constraint. For example, this quantity here, Gm, is the inverse of the filter function, which represent a physical phenomena. And
can you increase the zoom so that it looks
yes.
better? Thank you. Sorry.
This is the inverse of the curve of the monochromatic constraint of the value of f And this is a statistical function and output, and this filter function is weighted by the extended mass distribution to obtain a kind of average filter function, which represents physical processes. And also, as mentioned before, we introduce two new corrections, which considers, for example, the objects outside of this output or filter function. For example, this is the function obtained, for example, for strong lensing constraints is the inverse, and in the blue line is an extended mass distribution. If we combine this mass distribution, for example, with this integral here, we can obtain this kind of function here. But we have objects outside this region, this black line, and we need to correct our estimation of the fraction of primordial black hole has dark matter because the presence of this object. And the other correction is because the evolution of the mass function. For example, here you can observe an example of mass distribution, and the blue line represents the evaporation mass at redshift 0. This other blue line represents the maximum mass of the distribution. But now, if we consider the same extended mass distribution, but now at redshift 1000, for example, this evaporation mass is shifted to the left, is represented by this red line, and the maximum mass also. Then this extended mass distribution has an evolution if I consider this extended mass distribution at different redshift. And then we introduce a correction which takes into account this kind of evolution of the mass distribution to compute finally the fraction of mass of primordial black hole has dark matter, and the final expression to translate the monochromatic constraint to extended one is given by this formula 68, where the Cm is the correction because the objects outside of the output, and C theta is the correction because the evolution of the mass distribution, and this is the average output function or the filter function weighted by the extended mass distribution. I don't know if I asked the question, Ignacio.
Yeah, perfect. So just to clarify one thing, so the most important thing here is this idea that, let's say you're opening a paper of car where you have this actual table, right, with the constraint for a certain mass, right? So then you literally can export this table and transform it into a function, right? F as a function of m. And then the main point is that the inverse of the fraction can be interpreted as the output, right? So, so basically the idea is that the more constrained a region in mass is, it means that there is some underlying effect that is that is the most intense in that region, right? So the point is that an observational constraint is given by a maximum output effect in something, in whatever. So some observational constraint is given in terms of a maximum output effect. So if the allowed fraction is small, it means that the effect is very high with respect to the maximum effect allowed by the observational constraint. So it makes statistical sense to create a filter function just by taking the inverse of the fraction, so the inverse of f. And then the rest is just obtaining the average output, and then essentially you're doing a weighted sum of the fraction of the different processes for the extended mass distribution where you're computing the average of the output function for each of the constraining processes, averaging using the mass distribution, the mass function. This is like the main point. So just to clarify that.
Okay, thank you, Ignacio. More questions or comments? If not, we can start with the hands-on activity. I send a link. It's a GitHub link, and you can download the code, which contain extended mass distribution with a spike.
Maybe that game later, they didn't see the chat updated.
Okay.
So I will plot it again. I mean, it's also on the Discord page channel if you want.
Okay, I will send the GitHub link. You can download the code there. And in this repository, you can you have many files, are very similar to the Joaquin Sorera codes that they sent before. Actually, it's just a modification of this code. Well, one of the old version of the code. I understand that Joaquin now has a more general code. There are many files. For example, in this FCT log normal .py, you can found the extended mass distribution for the fixed conformal time scenario with a spike. Here for the horizon crossing, that now we discuss how to translate monochromatic constraints to extended one. It is you can find the algorithm here. For example, I will open this code. For example, here, this is the average output function G, which depends on the mass that we discussed before, weighted by the mass function. Also, we can consider different observational constraints. For example, here in the Joaquin papers, he showed this table in the first session. We use all these constraints which are important or which act at different ranges of masses, for example, from Big Bang nucleosynthesis to the large scale structure constraints, for example, strong density constraints, dynamical effects. And you can observe here in this table that some observational constraints, for example, GRB lensing, white dwarf, neutron star capture, accretion of primordial black holes, and gravitational wave, they have a star. And that means that these observational constraints are disputed in the literature. There are many assumptions to calculate the fraction of primordial black hole has dark matter. Then in the code, we can exclude this disputed constraint, for example, GRB, white dwarfs, neutron star, accretion, LIGO, with this flag using remove disputed true. I will show now a very short example. Well, in the repository, you can find also a Jupyter notebook here, FoF HC, spiky mass function. This notebook is just for the horizon crossing mass function, but you can introduce or you can modify this Jupyter notebook to calculate, for example, the same for the fixed conformal time scenario. This is the Jupyter notebook. There are standard models here. I write the math function. If you can check, for example, the code, the constants, for example, CHC are given in the Surera papers in some part of the text. Well, here, for example, the equation 43, and this quantity here, nu star, nu m, are defined here. First, we need to define a cosmology. That means that we need to fix the cosmological parameters. The default cosmology is the Planck cosmology, are the values of the cosmological parameters estimated by Planck. I will run this line. I define my cosmology. Now, I need to define the free parameters of this kind of extended mass distribution. For example, here I fix the M star parameters, I fix the blue index parameters, and in this case, I fix also the peak mass, one order in magnitude less than the position of the characteristic mass, and also I fix the amplitude A2 equal to 10 to 23 by hand. This amplitude A2 doesn't have a physical meaning. Putting this value or fixing this value, now I can create my mass function. I only have to load the definition of the mass function of these files here and on the repository. I fix the free parameters, and for example, I can now I construct the extended mass distribution. I can plot this mass distribution. I can fix the limits, for example, the lower limit in the y-axis, for example. And you can see, for example, here the spike. I can consider other value for the amplitude A2, for example, I 35, and I get a more spiky mass function. For example, if I decrease the low limit in the y-axis, for example, you can observe the spike. How to change this mass distribution. Also, I can calculate the same quantities that Joaquin explained before, together Nelson, for example, the cumulative number density, the mass density. For example, if I can calculate the number density of this kind of this mass distribution, I need to perform this integral here. Is the integral of the mass function from one mass m to infinity, and you can define, for example, those limits, for example, the limits of this integral, for example, from the evaporation mass, also is part of the code. Joaquin explained that in the third session. For example, I calculate the number density. I can plot the number density also, and I can observe different features which depend on the position of the spike and this, or the position of the peak and the primordial power spectrum, and also depend on the amplitude of this spike. But I mentioned in the talk, up to now, this value of the amplitude A2 is by hand, but now I can calculate the maximum or the amplitude to obtain the maximum mass, the maximum fraction mass inside the spike with respect with the total mass of the distribution. And there is a routine in the code, for example, find A2 max restricted. if I use this function for this extended mass distribution with this free parameter, I will obtain the maximum amplitude A2. Also, this function returns the maximum, the value of the amplitude A2 and the maximum fraction of mass inside the spike with respect to the total mass of the distribution. In this case, is 45% of mass inside the spike with respect with the total mass, and the value of the amplitude A2 is 4 to 10 to 22 in this case for this value. When I calculate, for example, this in this way, the amplitude A2, the algorithms fix this value like the amplitude of the mass distribution. For example, observe here, if I change the position of the peak, for example, 10 to 3 times the characteristics m star, I need to create my mass function, and then I can calculate the new amplitude A2. Now is 8, 10 to 20, and the fractional mass inside the spike is 16% of the total mass of the distribution. Is less than the last case. If I put the peaks far away the characteristic mass, I obtain less mass inside the spike that if I put the peak mass very close to the characteristic mass m star. And also, for example, for this configuration, I can create an array of the position of the peak of, in this extended mass distribution. For example, here, just for example, I put a position for the peak with respect with the characteristic mass m star. I will compile this line here. Now I can calculate for this array of position of the peak, I can calculate the amplitude A2 will provide the maximum fractional mass inside the spike. I will run the code. It is very fast. This code is based on the version of Joaquin codes. He sent the first session, and Joaquin optimized very well the code, and this is very fast. Now I have a vector. I can print a vector of amplitude, maximum amplitude A2 for the different positions of the peak. And this amplitude will provide this maximum fraction of mass inside the spike. Sorry. Sorry. For example, you can observe like the fractional mass inside the spike varies vary with the position of the peak. The fractional mass inside the spike is less than less than these cases when the peak mass is very close to the characteristic mass. In this configuration, the maximum fractional mass inside the spike is 60%, more or less. And also I can calculate, for example, diffraction of PBH, or primordial black holes, has dark matter using this maximum value for diffraction and the maximum value for the amplitude A2 for the corresponding position of the peak. And I, as mentioned before, I can consider all the observational constraint, all the monochromatic constraint. For example, here is this case, considering all the constraints, but I can remove the disputed observational constraints with this flag, and I will obtain different values. I will run this line here. Now I calculating the fraction of primordial black hole has dark matter for both cases, using all the observational constraints and removing the disputed one. I print, for example, the position of the peak, the amplitude, which provide the maximum fraction of mass inside the spike. And you can observe also that if I consider the disputed one for the calculation of F, vary in this quantity F. For example, this column true is when we remove the disputed observational constraint. In this case, we obtain higher values for F in general. Also, I can calculate the fraction of mass of primordial black hole has dark matter when we don't have a spike in the extended mass distribution. I mean, when I recover the extended mass distribution from the broken power law. In this case, I put here the amplitude A2 equal to 0, and I obtain a value, is 10 to 3, more or less, and also I can show these results in this kind of plots. Here, the position of the peak, the fraction of primordial black hole, the fraction of mass of primordial black hole has dark matter, and the colors, the dots, represent the fraction of mass inside the spike with respect to the total distribution. And as mentioned in the talk, this line represents this value with the amplitude A2 is equal to 0. And of course, the value of FPBH can increase or decrease depending on the blue index, depending on the position of the peak, also depend on the M star, the characteristic mass. And you can explore how these points change depend on the values of the free parameters. And there are some activities that you can do. For example, compute plot, for example, this point here, but now removing the disputed observational constraint. Here I plot the case of when I consider all the observational constraint, but you can see that also I calculate this case. Also, you can vary the blue index. For example, you can consider 3 values of the blue index or 3 values of the characteristic mass. And you can also create a vector of position of the peak mass, for example here, or you can create a vector with more resolution, for example, to have to observe the behavior of how to change this kind of plots for many peaks, for example, for many values of the peak. What else? Well, you can try to obtain this kind of plots for the fixed conformal mass function, fit conformal time mass function. This is the expression. When we apply the primordial power spectrum with a spike in the Press-Schecter formalism, we obtain this analytical expression. If you read the Surera papers, you can find the value of this constant CFCT, and you can substitute in the code. Well, the code includes this constant, and you can also define this function, nu stars and nu m, that appears in these terms, nu star and nu m, and you can explore how this value changes for this fixed conformal time mass function. What else? There is are there questions or comments?
I have just one comment. So doing the weighted average of the 1 over f, each process, right, each physical process will give you a constraint. So once you have one for each physical process, how do you combine them to find the net one, let's say?
Okay, we combine them by, well, using an individual monochromatic constraint. This will provide a value of FPBH. To obtain the total value for any configuration, for any mass distribution, we take the minimum value of all the monochromatic constraints. For example, you can observe that in this script here, mass function.
Or you can just show the files in the GM folder. Those files are each file is one line in particular. Corresponds to one operation.
See, for example, here first we compute df for one observational constraint, but in the end we take the value of this. We take the minimum value of the array of this quantity obtained with a different monochromatic observational constraint. For example, like Joaquin said, in this repository there are all the files of this output function or the filter function, the inverse of the curves of 1 over f. For example, we have all the observational constraints in the table of the Joaquin papers are the same observational constraints presented by Carr. For example, this is for Big Bang nucleosynthesis, for example. Here we have the mass of the primordial black hole, and this is the value of the 1 over f. Then we weight this output function with the mass distribution. We obtain a value for f. And we repeat this procedure for all these output function or for this filter function. We obtain then about I don't know 15, 20 values for f, and then we combine and we take the minimum value. And this minimum value of all the observational constraints is the value for the extended mass distribution.
Perfect, thank you.
Sorry, in this part of the code, we do that. We take all the f value from the different observational constraint, and we take the minimum value. And also here we can remove the disputed one, or we can consider all the monochromatic constraints. I don't know if we are more questions or comments about the code. Well, just to mention an interesting thing about this standard mass distribution with a spike is that to calculate, for example, the number density or the mass density, for example, to calculate this quantity here, we need to perform integrals. But these integrals are very sensitive to the spike. We need to, for example, we need to have high resolution in this region of the spike to get a correct value for the integral. And then to avoid these kind of numerical problems, we perform the integrals in different parts. For example, the integral from this limit here, the evaporation mass, for example, here in this position where the peak starts. And also we perform other integral to calculate, for example, the area of this mass to this mass, for example, covering the peak or the spike. And after that, we add the value of the integral between this mass and the maximum mass of the distribution. And this is a modification of the Joaquin code, for example. And this is reflected here in this file, the mass function file. We separate, for example, the integral, for example, of the extended part of the total distribution. We have, for example, a function for the spiky part. After that, for example, to calculate the total mass density, we add the results of these integrals to avoid these numerical problems. And this is a modification of the code that Joaquin sent on that last Monday. Joaquin?
Yes, maybe I have one question. Maybe can you explain why don't you get exactly 100% of the mass in the spike? Maybe it is possible to put all the mass in the mass function within the spike. And if not,
Well,
why that happens?
Yes, up to now, the maximum fraction of mass inside the spike that when I explored the free parameters of this configuration is about 70-80% of the total mass distribution. But this happened when we put the peak mass very close to the characteristic mass. But beside that, we have this constraint. We compute, for example, the total mass inside the spike first because we have an extended part, and the addition of the mass of the extended part with the spike should be satisfied this relation. Because we think that these hypothetical objects can be composed the dark matter in the universe. Then we put this limit. The mass density of the configuration should be less or equal to the mass density of the dark matter in the universe. Is because if you exclude this physical condition, you can put the total fraction of the configuration in the spikes, because, for example, here you can see that the amplitude, the mass function for lighter primordial black holes decrease, and then this lighter primordial black hole don't contribute significantly to the total mass of the distribution, for example. And then you can put more mass inside the spike, but you have this condition, you have this physical condition. Is for this reason.
Okay, thank you.
Mm-hmm. More question or comments?
Well, maybe if I'm allowed to say this, if you have any other questions regarding any part of the workshop, first day and the other days, you can put them in the Discord, so we can have a chat about that. And if any problem arises, then you also can tell us about that.
Mm-hmm.
We're going to also put there the links for the videos.
Mm-hmm.
So they're available soon. We didn't manage yet. But yeah, I mean, I guess the people can play a little bit, and for sure they will have some questions.
Okay.
Okay, I take the opportunity to thank you really. I mean, I really enjoyed the workshop. It was really nice. Okay, I will